You have made it back to boot camp. We're gonna go over homework today, and then we're going to touch on some stats. As a reminder, this is the halfway point. If you kept up so far with all of it, you've learned Python to the extent we've taught it so far. That's big, that's huge. So congratulations. If this is a refamiliarization for you, if you went through Stats 101 or some sort of intro to stats, this is all gonna be familiar. But if you've never seen any statistics in a statistics course before, this is gonna be a little tough. You're not getting kicked out, it's all a free course here, but I'm just not gonna go over in depth what certain things are. I'm gonna walk everyone through question 1 because you're gonna need it for today. Okay, so we're gonna create strikeout. So the statistics strikeouts per 9 helps contextualize how often a pitcher strikes out their opponent over the course of a game. Calculate strikeouts per 9 for each pitcher by adding the number of times a pitcher strikes out an opponent, divide by the number of innings they threw in, and then multiply through by 9. So this is just like ERA except strikeouts, right? So okay, so we have our ERA data frame. .head. Oh shit, I didn't load in. You caught me lacking. You caught me lacking. It's okay. See? Even I am unprepared for day 5. We load in our ERA data frame, and we just take a look. Like, we have runs scored in innings. Now what we need is strikeouts, right? So let's go get strikeouts. First, we do have this other data frame, df2, if you recall, which has runs scored, number of pitches thrown, all this other stuff. df2, that comes from over here. This is where we made df2 for the runs scored and then ERA stuff, right? Similarly, we're gonna use this basically exact same thing, and instead of doing runs scored, we're gonna change this out with strikeouts. So the first thing we need is a strikeout column. So let's do the thing we've been doing for a while. Get strikeout and turn it in to... It's in events, okay? Now, there are 2 strikeout events. And let's just make sure we have both of them in there. There's strikeout and there's strikeout double play. So let's make sure, so if you didn't catch that before in the homework, if you didn't see that before, you could always go to events unique, and then see all the times it says a strikeout, right? So we have strikeout and we have strikeout double play. So let's make sure we get both of those. Strikeout, strikeout double play. And this is just like what we did in day 1. All right, we'll do is in strikeout events, strikeout equals 1. This is the way that we're teaching it in here. There are other ways. If you have another way to do it, feel free, so long as it's getting all the data that we need, right? We create our column for strikeouts, and then you could always check, of course. You take a df2 head here. At the over here, strikeout, and then you have a 1 here, and you have a bunch of zeros. If we check the top 20, you have 1 here, and you have another 1 down here. In row 8. So we have our strikeouts, and now what we want to do is we essentially want to do this exact same thing except for strikeouts. So we'll have df2, and then we'll do pitcher name, pitcher, because of the ID, right? We don't want to double up on any particular ID. We'll get strikeout in there now. We'll group by. And then we're grouping by the pitcher name and pitcher. You could even just do pitcher if you want. You could even just do it this way. And this would work as well. So if you just did the pitcher ID, that actually works as well. So some of you did that in the Discord. And then, of course, we'll sum over all of this stuff. And let's make a temporary data frame to store it all in. Okay, so we're gonna do a group by over the pitcher pitch ID and their name. Sum all their strikeouts. Now, and so what this looks like, if you do a DF head here, you should have pitcher name, pitcher ID, their unique ID that relates to who the pitcher is, and then the number of strikeouts they threw in the season. Now, remember, in our ERA data frame, which is where this is gonna join to, we already have pitcher name and pitcher. We also have innings already. So we don't have to worry about dividing by, we don't have to make another statement to divide by innings. We just have to use this one statement here to get our strikeouts. And then if we merge all of this onto ERA, we're actually nearly done. So that's what we're gonna do here. We're just gonna take ERA and we're gonna merge. And then of course, let's practice good coding practices. We'll merge onto pitcher name and pitcher. And then we could overwrite ERA, but if you're afraid to overwrite your ERA data frame, you could always just make a temporary one for now. And you could double check. Did everything merge right? It looks like it's okay. There's no duplicates. And then if we look at the shape, 632. And if we look at the shape of the other one, we may lose a couple, but that might be okay. No, we don't lose any, so it's just 632 straight up. Okay. So this merge is good. We're adding a column essentially. So let's just overwrite. So I'm gonna run through this now. And now we're gonna have a new column. And then if we do our head here, you'll see we have strikeouts. So now we just have to finish out the rest of this. So we're just gonna use this same equation here, runs scored divided by innings, multiplied through by 9, and that will get our strikeouts per 9. Baseball's a little weird, and I'm gonna call this, or I'll call it K9. Woof woof. If you call this strikeouts per 9, that's fine. If you call this K per 9, that would work too, but your database people might be angry at you if you push this up to the database. So we'll do strikeout, because that's the column here. And then we're gonna divide by innings. And then we're gonna wrap all of that, and we're gonna multiply through by 9. It's for the statisticians out there, when you hear strikeouts per 9, you might think like, oh, this is like every 9 innings, how many strikeouts are there? True, but some of y'all might think like, since it is like the notation online is K divided by 9, some people conflate that with like a division of 9. The notation's a little goofy, I must admit, but it is what it is, I suppose. So we'll do K per 9. And now if we look at ERA head, we'll have our K per 9. Okay? So how many strikeouts they throw per 9 innings. And if you want a bigger look, let's look at the top 20 here. So someone like Sandy Alcantara, who I believe was didn't Sandy Alcantara win the Cy Young in 2022? Let me see. Yeah, Sandy Alcantara. So he threw a lot of strikeouts, and he also pitched in a lot of innings. His strikeout per 9 is pretty good. Okay, so that's how you do homework 1. So we do need everyone to have strikeouts per 9 in their ERA data set today. Some of these things, like notice where the ERA data frame, because we ended with the ERA data frame creation on day 4. So if for whatever reason it doesn't look like this, you might just want to run your ERA data frame again and then run all of this code again. And that will get you your K per 9 and your ERA column. Some of you may have just combined everything in your homework into one thing. That works too. Okay, question 2. So I saw some people do this, similar to ERA, where you have home runs, walks, strikeouts, innings pitched, plus 3. So using the ERA data to calculate fit for each pitcher. So one thing you need here, obviously, is the Ks per 9, or sorry, strikeouts. But you also need walks, right? You also need walks. So we're gonna get walks in there first. First thing I wanna do is df2, I'll check my events. So we have 1 walk event. That makes it really easy. So walk. My events can be equals walk. Walk equals 1. And then I'm going to make this data frame. I'm just copying stuff from the answer here in question 1. Now this is walk. Notice I'm saving over this temporary data frame. And then we can merge this onto ERA. Okay. Same thing, just with walks now. So when we run this, you'll have a column for walk. So now you have strikeouts, walks. Now you also need runs, or now you also need home runs. So one more time here. I could actually just do this all in here. Home run. I believe the event is called home run. Now, you could have just done it this way, where now you're doing a sum over both walk and home run, and then merge. So in this case, I'm making one column for walk, another column for home run, and then doing the aggregation over both, and then merging back. So I'm just gonna rerun a few things here just to make sure I don't double up on anything. So I'm gonna rerun my ERA the first time we did it. I'm gonna rerun my strikes per 9 because we'll need that. And then I'm gonna run question number 2. And so now we have strikeouts, walks, home runs. And those are the 3 things we need for the equation I gave y'all at the top. And then the bottom, innings pitched, that's number of innings. Okay, so once we have all 3 of those, we could actually just do this all in one go. So we need home runs. And then this is times 13. This is the equation. Let me rip this equation. Just put it down here for now. And then we're gonna add ERA walk times 3. Okay. And then we're gonna subtract ERA strikeout times 2. Okay, wrap all of that in a parentheses. And then we're gonna divide, and let's wrap this in a parentheses too. ERA and innings. And we wanna wrap all of that in one big parentheses. And then we do 3 plus all of this. Okay. And this is FIP. Okay, now when we take a look, now we have FIP. And FIP and ERA, we'll get there in a second. I'm gonna show everyone one other way to do this. Again, a lot of people are fine using pluses and asterisks, slashes, minus for your arithmetic operators, but I'll show you something in pandas that could keep your code pretty clean. So notice how we have like a home run column. Now if I wanted to add, or if I wanted to multiply by 13, like I just do home runs times 13, just like how the equation says, home runs times 13, right? However, there's also built-in pandas functions for multiplication, and you could do the function mul, short for multiply, and then put in the number you want here, 13, right? You could also do this with adding, right? So we could add, if you added 13 to everything, you would get this. Here's the original, right? 12, 1, 2 is the top three numbers. If we add 13, 25, 14, 15 is what we get. And again, this is no different than if you just did plus 13, 12, 14, 15. But the benefit, this is multiply. The benefit here is readability. Now, let me show you. So we do this multiply by 13, right? And then we gotta add. So we're gonna do this equation again. So home runs multiplied by 13, and then we'll wrap that just like how we wrap it here. Then I could add, and then I'm adding this statement here. ERA walk times 3, but it's mul 3. And then it's this next statement here. So I'm gonna do subtract, and then it's strikeouts times 2, mul 2. Okay, I guess I didn't need this parentheses. So this is all the top. Now I could wrap that just like how I wrap it here, and then I could divide div by innings pitched. Okay, then I could wrap all that again and add 3. And now we get the exact same thing that we got here, except we're using the built-in pandas multiply, add, subtract, divide. Okay. And you might be wondering like, well, what's really the difference? Okay, so if we wrap all of this in a parentheses like we have been doing, we could actually put all of this on different lines, right? Right. So now we have this statement, then we add this statement, then we're adding this statement, divide all of that, and at the very end, add 3. And that is the same thing that we've been getting before. So this makes it a little more readable. You could do that here. You could obviously wrap things and put them on different lines and use like a backslash if you want. But just showing you 2 different ways. Okay, number 3 was explore the Seaborn Gallery page. Now, this is just for those who are trying to get into data visualization side. All these data visualization packages, whether it's in Python or R or Rust or Julia or whatever you may be using at the end of the day, you'll have example galleries, right? So like, here's like a different way to display like 3 different scatter plots if you wanted at the same time. Okay. Here's a way that you could plot multiple things in multiple conditions, all in one graph, right? Here's what a heat map could look like if you're doing like correlation plots or something. So this is all like good for statistical inspiration for your data viz. I gave a couple examples, so I'll just use joint plot and KDE plot for FIP and ERA. Okay, so if I go Seaborn joint plot, data equals ERA, X equals ERA, Y equals FIP, and then I'll just do a plt.show. So here's a joint plot. So this gives you your histogram on the joints, and then a scatter plot here. Okay, so that's pretty nifty if you wanted to see some stuff at the same time. And then also KDE plot. If you wanted a bivariate KDE, you could do it like this. So just changing the word KDE. Notice how interchangeable this stuff is, right? Some things should just be really easy. And if you want to make it like even fancier, there are all sorts of different things you could do, like inside of a KDE plot, for instance. There are all sorts of different things that you could play with in the keyword arguments. For instance, if we wanted to fill, so rather than just having contour outlines, if we wanted to do a fill, you could actually just say fill equals true. And now you have like a nice filled density plot. And it's the same here with a joint plot. If you wanted a regression line, you could type in the keyword argument kind equals reg. And this will change that scatter plot into a scatter plot plus a line of best fit. Hopefully people had some fun exploring some data viz. All right, that's the homework. Let's dive in to our stuff today. Okay, so the first thing you do, let's just make sure we all have the same ERA data frame, the one that we did from day 4. I just copied all of the code we did on day 4 and the stuff from the homework, and I just pasted it into this notebook. So when I run this code, it's gonna overwrite our ERA data frame. It's just gonna remake it every time. Okay, so your ERA shape should look like 632, 10, and then in terms of the first 10 rows or 5 rows, it should look something like this. We're gonna go over some things, and we went over a few of these things before, but remember some basics. Let's just say if we wanted to look at FIP and ERA, okay, and let's put in our K per 9. So if we would just want to look at 3 columns, FIP, ERA, and K per 9, right? We could do this as scribe. We did this the other night. We used describe, and that got us our count, how many rows there were for this data, our means, so the average FIP, right? The average ERA, the average strikeouts per 9, our standard deviations, the min value and the max values, right? Min and max here, min and max. And then our interquartile range or percentiles, 25th percentile, our 75th percentile, and the 50th percentile, which is also known as the median. Okay, so that's one way to describe our data, right? Now, I showed you that last night, but let's show you a couple other things too. So if we just wanted to do ERA and we wanted the median, right? You could just type in median. Dot median parentheses, right? And this number here, 3.16 or 3.613 for ERA, that's the same here, 3.613 for ERA, okay? You could also change this to quantile, okay? So like a percentile, quantile. And if you type in 0.5, you should get the exact same number, 3.613. And that's the same here, because that's the 50th percentile, right? If you did the 25th percentile, this number is 2.78. That's the same here, 2.78. If your numbers are a little different because your rows might be off or something, like for some reason, even though your numbers might not be the same as mine, you should be able to get the same numbers from the quantile here and the quantiles inside your describe, right? You might ask, like, well, could we do other numbers? Like, could we do the first percentile? You totally can. You could get the 99.99 percentile if you want. So feel free to use quantile to get your way to percentiles if that's something you need. And of course, other things, this is 69, okay. Another thing is, we do know how to do mean, because we've been doing it in the group by, right? And then something that some people have asked in the Discord, some people use mode when we did one of the homework problems. Some people use mode, and you can actually use mode as well. So you can use mode, and notice how for ERA mode, there is an ERA of 3 and an ERA of 4.5. So mode is the most frequent value in this column of data in this series. If it's tied, if it's like, the number of times 3.0 and the number of times of 4.0 or 4.5 are the same, then it's going to return both of them, right? So it's not gonna scam you. It's not any shortcuts here. Statistically, you're getting all the stuff that you would typically use. If you're trying to report some of this stuff, if you're, say, doing like a research paper, if you're coming from the world of academia, any of that stuff. Another thing you could do in the pandas data frames, say we have the same data frame, FIP, ERA, and strikes per 9. And say you just want to do a correlation. Like, what is the correlation between all this stuff? You could actually just type in .corr, this function, core. And this actually will do Pearson R correlation over these columns. For those who are like, I kind of know correlation, remind me. The positive numbers means it's positively correlating. So as FIP increases, ERA is also increasing positively. If it was a correlation of 1, then for every time FIP would move 1 value, ERA would also move 1 unit as well. 1-to-1 correlations, right? So FIP and ERA, there's a correlation here. There's also this negative correlation, FIP and Ks per 9, which makes sense. As you become better, as your FIP decreases, lower FIP's better picture, K per 9 should increase, right? So as FIP increases, as you get worse, your strikeout rate decreases. Your K per 9 decreases. So that kind of makes sense, right? And then you see this diagonal of 1s here. This diagonal of 1s, that's just FIP correlating to FIP. That's the same value. ERA correlating to ERA, that's the same values. And K per 9 to K per 9, that's the same values. You should see this kind of behavior, right? If you didn't see that, then something is definitely wrong. So this is our correlation table. Okay, this is R, or Pearson R. For those who are like, Pearson R, isn't there another name for that other than R correlation and Pearson R? Yes, it's the Pearson product moment correlation coefficient. Thank you for asking. So another thing you can do, just, quick and dirty, rather than correlation, R, you might be in the world where R squared is something that you use to report. R squared in very most broad general statistic stuff would be the explained variance. So how much does this particular variable explain the variance of another variable? You think of it as in terms of percentage. Also, sometimes you may have heard this term effect size. Some people may use R squared as an effect size metric. So not just how significant something is, but also how impactful is it on the data set. The stronger the effect size, the more important the statistical finding is, or the more evidence there is the statistical finding has some sort of correlation or some sort of evidence in one way or another. So the way you would do that is to, some people are like, I used to get this question in chat, I still do. Some people come in and they ask me, how do you calculate R squared? It's very simple. If you have R, which is correlation, our Pearson R value, you square it. You just raise it to the 2. And that gets you r squared. I'm not even joking. That's r squared. R squared is literally r raised to the 2. So you could just type in 2 exclamations here. So you wouldn't type in this. If you typed caret 2, you're gonna get a bunch of weird ass shit. Python uses the caret for like some bitwise operation. Python isn't a statistical programming language at heart. Python is like a jack of all trades language used in like web development, app development, game development, database engineering. So some of these operations inside of Python are not necessarily meant for mathematical operation. So its double asterisk is power or exponent. So if you wanted r straight up in your table, you could do a correlation, .core. If you wanted r squared, you could get that same information. Some people report Pearson R and also r squared. You get that info too. So one other thing, you know, in the world of business intelligence, in the world of business reporting, a lot of the time you might be someone who works at a company and they like putting things on a 100 scale. 100 would be the mean, and then plus or minus whatever above or below 100 is would be a percent increase or decrease. Like 110 would be 10% above the mean. That way it arbitrarily sets a value for what a statistic or a metric is without having to know, like, oh, well, the mean ERA is 3.69, therefore an ERA of 3.8 is like, instead of that, you could talk about things like, oh, the mean ERA, if that's 100, another pitcher who's 110 would be 10% greater. And in this case, that would be worse, right? So stats like WRC plus and OPS plus, exactly. So let's just create a plus metric. So we'll do a ERA plus here. You could also call it ERA plus. I'll call it ERA plus here. Plus metrics are so easy. I see this all the time everywhere, okay? So we'll just take our ERA column, we're gonna divide by the mean. And you could basically stop there if you want, but if you worked at a company where it's like, oh, take that out of decimal and move that into 100 scale, let's just multiply through by 100 to make sure. So now if we take a look at ERA head, we have our ERA plus metric now. And yes, if you wanted to do a plus with an actual plus sign, that would work as well. For posterity here, this is good coding practice here. Let's leave out the special symbols here. And again, if we wanted to describe ERA plus, and we took the describe here, we could see the mean is 100, 25th percentile, that lower box of the interquartile range, 75. The upper range is 120. The median is actually 97. So the mean and the median are different. The worst pitcher is going to have the biggest number because bigger numbers are bad, right? But you do have pitchers with an ERA plus of 0, who apparently should be very, very good. So if you are coming from the business world and you need to adjust things into your plus scale, you can do that, and statistically it's going to come out like this, right? And sometimes you need to report like, hey, this plus scale, it has standard deviation of 36, our interquartile range, things outside, things lower than 75 is good, things above 120 might be bad, right? So let's also just describe this one more statistical way for now. If we look at the histogram of it, if we use SNS hist plot, this will give us a histogram. statistical exploration isn't just statistical numbers, but it's also visually describing our statistical distribution. I always like using a histogram, as easy as it gets, right, to plot the distribution, just to know, are we looking at something that is normally distributed? What's the outlier looking like? The context of this particular column, right? And now we're kind of putting together the story statistically in terms of our descriptive stats. All right, let's dive in to the academic statistic world. So let's load in some new packages, some new libraries for us to use in order to get some of these numbers, right? So we're adding to our knowledge of libraries here, right? So you have pandas, you got matplotlib, and you also have Seaborn. The first thing we did was operating system, or OS. Now we're gonna load in from scipy.stats. Again, if you're using Colab, you should have this. If you installed through Anaconda, you also should have this. Import, and we're gonna import 3 things, okay? First thing we're gonna import is Pearson R. That's the OG. If you are taking Stats 101, you're probably doing Rise over Run Pearson R stuff. Let's also load in Spearman R. Okay, for you non-parametric statisticians out there, just to give you a little taste of some rank correlation instead of our Pearson correlation. I know in the world of academia, we are moving away, or at least some of us, some disciplines are moving more and more towards Bayesian or non-parametric statistics and reporting that. So having a little non-parametric statistics under your belt, never a bad thing. Also, Spearman R doesn't get much easier than Spearman R. Just rank them in order, correlate the rank order. Let us not forget everyone's intro to stats statistic. Let's load in the t-test. This is called t-test underscore ind. Okay. Now there are several different t-tests to choose from. Like you could do your one sample t-tests. You could do some relative t-testing, but we're gonna use our independent samples t. All right, now let's load in one more thing, and we're gonna use a different package for this. You might be wondering like, oh, well, can't you just load in all the stats from the stats package? You could, but I'm trying to set you all up for the day 6 and 7 as well. So we're going to go into another another library called scikit-learn, and we're going to grab from scikit-learn sklearn.metrics. We're going to import mean squared error. Okay. Sometimes it's not always about how it correlates. Sometimes we want to know how much we're losing, what the loss is. So go ahead and run that. If you hit Control Enter or the play button or whatever you got to run that cell, this should all load in. If you're hitting stuff that says, you don't have this package, you don't have this package, you're gonna wanna install that. And of course, before we start diving into all this stuff, let's just take a look at the data set we're gonna be using. That's our era.head, okay? First, I wanna teach you a little Python stuff before we get into here, because indexing, or being able to select the thing you want, is something we actually haven't gone over yet. So you made it this far, and you don't know how to index anything in Python. So, congratulations, you've learned Python in the most wrong way when it comes to teaching Python from scratch. But it is important to know how to access information in a variable, because you might have multiple things like p-value, t-value, some sort of confidence interval information. You might have all this stuff inside of a function that it outputs. To get access to it all, you need to index it or be able to select it. Just like I'm going to select the information from column A, row 4. Indexing is important. So, for instance, if I just type my name, Nick Wan, x equals Nick Wan, right? And if I look at the print of it, Nick Wan, it comes out as a string. This is a string variable. But each value, or each string position, you could actually index. For example, if I wanted to get that first value here, Python is 0 indexed. So I could type in square bracket 0, right? This is not so different from your pandas conditional filtering. This is indexing in raw, your native Python environment. So if I wanted to get, say, the letter K, that's in the 4th position, but because we're 0 indexed, it's actually the 3rd position, right? So I could get that K with a 3. And if I want all the way at the end there, if I want my last value, that n, I would have to count like 4, 5, 6, 7, minus 1 because it's 0 index, so that's actually 6, right? So that would give me my 6 value. Now if you go over, if you're like, oh, 7, it's going to say that's out of the range, right? Because it's actually only doing 0 through 6, 7 values, right? So 0 through 6. Now, there is a trick, and I'll show this trick because it is important. If you wanted that last value, 6, but you don't want to count, right? Like, what if my name was Nick Wan 4 times, right? And I wanted the last value specifically. You could actually go backwards with your indexing. So if instead of saying 0, which would get me this, let's put a number in here instead. Nick Wan 69 for no reason. You could actually negative index. So if I wanted the last value in a string, you could actually type in -1, right? And notice how -1 gives me the 9. If you want the second to last, -2. And that gives me the 6. And that's going to be helpful because sometimes you don't want to count how long a certain thing is, how many things are in a particular list. You might just want to call it by the index, right? So for example, if you had a variables list, var list, and that had ERA, FIP, and K per 9 in it, in order to get, say, the first variable in this, right, you just say 0, just like we've been saying. But the second one is 1, and the last one is 2, or the last one is -1. And this is going to make sense when we start doing our statistics here, because you're going to get p-value and the stat value, right? So you need to be able to access the p-value and the stat value. So, for example, if we wanted to use the Pearson R, here we go. We're using Pearson R now. Surprise! We're using Pearson R, and we're going to type in ERA, square brackets ERA, to get the series, right? So the column ERA. And if we want to correlate that with FIP, we could run that, and now look at what we get back. We get the stat, the R value, 570, 0.570, and we get the p-value, which, although it seems large, let us not forget, this is e to the -56, so for you academics out there, I believe this is your triple asterisk, less than 0.01, less than 0.001 even. So you get both the R, the Pearson R value, and then the P value, which is functionally 0. So to double check ERA and FIP, 0.5703, you could actually scroll back up to that correlation table we had, right? That ERA FIP correlation, and we got 0.5703. Math is magic. So if you weren't convinced that correlation was giving you Pearson R, now there's a little confirmation. Another package using the Pearson R method formula, you can confirm. So there's your stat. Now, you could set this equal to a variable, just like how we set everything, right? When we load in data, we set to a variable. When I typed in my name, NickWin69, that's a variable X. A variable of a list of a variable list. So let's just assign this to R, right? Because this is the R value, right? This is the Pearson R value. And this is going to give you this Pearson R result, statistic, and p-value. Just like in a list, just like in a string, these are accessible by index, right? So if I type in R0, this is going to give me my stat value. And if I type in R1, that's going to give me my p-value. And if you want to be fancy, you could say, what's the last thing it's in this entire list? That's your p-value. So you can access the information inside of R using indexing, Python indexing. And if we wanted to create a variable called R squared, we could type in where the stat value is, Pearson R, is in that first index, and then raise it to the 2. All right, R squared. Remember, square is 2 asterisks. Okay, so now if we look at R, and if we want this all on one line to print, we could also look at R squared. So it's our Pearson R value, our R squared value, and if you want to throw in that p-value, you can throw in that p-value as well. Again, just using that Pearson R function, and we're going straight from our table, ERA and FIP, which we calculated at the beginning of today's notebook, using Pearson R. And now you have all of this statistical information that you could use. So you might be wondering, well, this was cool, but what about non-parametric statistics? It can't be that easy for the non-parametric stats. Let's go Spearman R. And I'm not gonna lie to you, it's the same stuff. It's the same way. This is why the world of programming for statistics is so much more accessible now than it ever has been. Because it isn't just the ability to put in data sets and do this simply, but the people working on these packages, computer engineers, software developers, the package maintainers, they're also statisticians, right? So they know in order for us to be able to get adoption for a statistics packages, they need to have really simple syntax that everyone can get along with. And so how much easier can it be than X correlated with Y inside of a function? And if that is the same representation in many different functions, then it's going to be widely used. SciPy Stats is probably one of the most widely used statistics packages out there in the computer programming world, especially in the Python. It's the number 1, I would assume, in Python. And of course, shout out to NumFocus. That is the nonprofit that is funded by the NSF that puts a lot of this packaging together. Okay, so if you want your Spearman R, this is your Spearman R. This is your non-parametric R. Or are the results different? Because this is Spearman R. This is not Pearson R. This is rank order correlation, not product moment correlation. Okay, and the same thing. So if I wanted my Spearman R squared, right? And then if my Spearman R value, my Spearman R squared, and my Spearman R p value, we get that too. And this makes sense because although the parametric stat has a stronger R squared, stronger correlation, there is some non-normal things in the distribution that may be inflating the correlation value. So to protect against outliers that might be inflating your stat, perhaps the non-normal distribution, a non-normal stat for correlation makes sense to use here. So a little weaker in terms of R, but still pretty strong. 30% explain variances is nothing to be scoffed at. And of course the p-value is near zero, functionally zero. So Pearson R and Spearman R, you could definitely have access to both of those. Again, something that's important is histograms. Right, so if we looked at the hist for ERA and we did PLT show, right? And if we did the FIP, you could also do FIP, right? But what if you wanted both? What if I wanted FIP and I wanted ERA? For plotting, you could actually just layer one plot. If you think of this as like a plotting sequential stack, that first thing we would plot first, the second thing would be plotted second, and then we're going to show both on the same plot. So if I wanted to plot ERA and FIP at the same time, you would just do two hist plots. So just like up here, we plotted just ERA, we're now plotting FIP and ERA. Let's get into everyone's favorite intro to stats statistic. Let's go to the t-test. Okay. This is a independent samples t-test underscore ind. And again, it's as easy as it's ever been. We're gonna do a t-test against ERA and FIP. Here's our stat result and our p-value. And this would make sense given the distribution. The means are the same, the standard deviations are the same, essentially. Well, ERA is larger. But there's essentially no difference between these two. That'll also make sense given the correlation. These things correlate very closely together. These are just two different numbers that are representing very similar info. So the t-tests in this case, overlapping, there is no t-value greater than 3 or less than 3. Our p-value in this case, not significant. So we could just call this t, and it's the same thing. If I wanted just the t-value, and if I wanted the p-value, right, just index through it. Now you might be wondering, all right, wise guy, that's all cool and all, but I'm here for something more specific. What about putting that information onto the graph? You academics out there want it all in one place. You know, what's it gonna take to show the study section that I got results from my pilot study? Let's put this in the title. Let's do plt.title, and we're gonna use something called an f string. Okay, so I did this before on day 1, and I said we'll learn about it a little later. So if I wanted to say like a value, like how I'm printing these things, you could actually type in like something like t value, and then you could type the number out if you wanted to, right? 1.692, and then this would give you a string that says t value 0.692, right? But if you wanted to do this algorithmically, if you have an f in the beginning of your string, and inside the string, you have those curly brackets, the curly braces, and you type in t0, which is what we have here, right? This is our t value, our t statistic. You'd be able to get the same thing. No harm, no foul if you're just copying and pasting into a string. You could definitely do that. But if you're doing this for, say, multiple comparisons, say you're doing a replication and it's like a multiple lab thing or a multiple site thing, you might want to bring in the data, run through your pipeline and get the same stat from different sources. You might want to use f strings for this. What was the f for again? To access the f string, if you don't have this f in there, and you just had it like this, this would treat all of this as a string. So you need the F in the beginning in order to get that value back. One more thing for those completionist academics out there wondering, like, okay, well, that's nice and all, but can we get that down to like 3 sig figs here? I got you, buddy. Python has a function called round. If you type in a comma after, you could actually just do the number of decimals you want to go out to. If you want to go out to 10, you go out to 10. If you want to stick around 3, if you're a physicist, maybe 6 is the number you might have to report. Okay. And you can put that inside the curly brackets too. Okay. So I have a way to type in my t value, and it comes out as a string. So let's imagine in the title, maybe this is like my chart. It's just a string. Maybe instead of my chart, I want to call this like ERA fib. You could also, this is going to take a, if you wanted to make a new line, that's \n. You know, cool. So now, ERA fib \, now you see cool in there. What if instead of cool, put an F in the beginning of this, and we just take all of this, and maybe we want to do this again. And instead of a t value, you get the p value in there? Cooking with gas now, chat. So we're able to describe something, plot it, able to put a title in there, and that gives us all of our reporting statistics in there. That's pretty good. Let's do it again with a different plot, okay? Let's do it again with a different plot. Let's do a scatter plot. Our good old friend scatter plot. You should be pretty familiar with this one, because if you did the homework, maybe you did something like this, ERA and fib. Okay, and we have our Pearson or Spearman values. So we want to do title, F string. This is ERA fib correlation. /n, this is like, you know, programming for new line. Pearson R. This is R. And then we want to round, of course. If you want to be a little fancier, maybe in parentheses afterwards, you got the significance. Do that with Spearman. It's all the same stuff. I'm just going to copy literally all of this. Except this is SR. Not bad, right? Let's put this all together. Say I wanted Pearson R. Say I wanted my Spearman R. I'm just going to copy this all into one cell. Say I want my t-test. And the one thing we didn't do yet is mean squared error. Mean squared error, same thing, y'all. If we did mean squared error, this isn't as fancy as the other things. Doesn't give you a ton back because it's just mean squared error, it's just a loss metric. Doesn't give you any significance value with it here. And if you don't want just mean squared error, if you want root mean squared error, you could just raise this to the 0.5, right? Root, square root is raised to the half. So now we have RMSE. Now we can put it all together, and sometimes like when we put it together, like the line of like you kind of could get lost if it's all in one line like this, right? So we're gonna make its own variable, and that way we could kind of edit the line a little easier. Okay, so I'm gonna show you all some new notation. So you might have noticed sometimes you could put a string. You could put a string with single quotes. We've seen us do double quotes now. I'm gonna show you a new way. Triple quotes. Okay. This is still a string, but inside of the string, maybe you're using single quotes or double quotes. Like if you wanted to use a string and use single quotes inside of it, now you have this triple quote kind of protecting you. That way you could access certain characters you couldn't have before. Okay. And yes, if you put an F in the beginning of it, and we look at R, it's gonna give you your F string. So we're going to use this to our advantage. We're going to use this to our advantage, and we're going to create our string and break it up on multiple lines. So we're going to be able to break this up on multiple lines. So if I type in ERA times fit, and I run this now, notice how it's giving us our /ns. So now we could kind of type more freely. Like here's my Pearson values. So it's now putting in those /ns for us. You can kind of see there, it's also rounding it off, right? So this is good, because now you can just type, and in parentheses, maybe I want my R squared in there. We want R squared in there, okay. What if I also want P? All on one line. And we could do the same, Spearman. And this is just S's in the beginning. I think, did I do SR too? I'm guessing I did. I guess we could run it and see. Yeah, Spearman. T values. Oh shit, did that wrong. T-test, T, and the p-value. RMSE, why not? And notice how they're putting in all those new line breaks for us. Okay, so we could just kind of write it more plainly with our triple quotes F string triple quote, and then each line, kind of more like how you would think about typing it out. And now let's do all the scatter plot stuff. PLT title string, PLT.show. Maybe you want to get even a little fancier. Rather than just a scatter plot, you want the line of fit like we did in the homework. So instead of scatter plot, you could type in reg plot, R-E-G plot. And if you ran that, you get that line of best fit. Do you have time for one more thing, chat? I know I'm kind of going over time. It's 10, but I want to show you all one more thing, and it's going to set you up for day 6. All right, one more thing, chat. And then homework, yes. One more thing and then homework. So we have a way to make graphs, near academic standard graphs, right? You have titles, you have how to report statistics, you have all the different statistical info, and visually how to display that info. In the world of academia, what if you had another data set with the same info and you wanted to run the same stats? What if you wanted to make this and turn it into something you reuse? Like for instance, we're using 2022 data. What if I wanted to do this exact same thing for 2021 data? What if I wanted to do it with this year, 2023 data? What if I wanted to do it for any year? Maybe we would want to functionalize this, right? Turn this into something where I don't have to type all of this. Rather, I would just have to make sure I could run all of these things one time, similar to like typing one set of functions in that for loop we did not too long ago. Write the code once, input new variables, new data, and show it in multiple ways, right? So let's showcase wrapping this all into a function. I told you today, I secretly said today was going to be really heavy on stats. And I think it was. And we also did data viz, but secretly we did a lot of Python today. So today was a heavy Python learning day. So let's create 2 different data sets, okay? Let's call one data set, let's make a new data set based off our ERA data, right? So ERA.head, we're gonna use this data set that we've been working on. ERA.head, the shape of it's gonna be around 600 rows. One thing you could do in a data set is sample randomly. You can randomly sample rows. Like if I wanted to randomly sample 10 rows. If I wanted to randomly sample 10 rows, I could do 10. If I randomly sample 6 rows, there's 6 rows, random. Every time I run this, it's random. If I wanted to make it so it's random, but I want to make sure that it's the same, call it 10 people every time, you can type in random state, right? And let's just do random state 1. Okay. So every time we do random, so this is random state 1. Every time we do random state 1, it's going to be the same people every time. Okay. And if we did random state 2, it would be a different, theoretically different sampling. And if we go back to 1, of course, it's that same. So let's make 2 different data sets. And I'm going to make them pretty specific names. So I would appreciate if you use these variable names for this. What if we use one data set and we call it the train data set? Okay. For the machine learning people out there already, they're like spidey senses tingling. And then let's do another data set called the test data set. And we'll use random state 2 for that. So we have one random sample of data, and then we have another random sample of data, okay? Okay, so we have one random sample of data, train shape, 100 rows in there if we look at the head, right? And then if we look at the test data, use the shape, it's 100 as well. And if we look at the head, different. Okay. So 2 different samples of data from our ERA data frame. Now, what if we want to do all of this over these 2 new data sets, right? Over these 2 new data frames. So one thing we would do is, like, if I copied all of this and then I put into each place where it says ERA and replace it with train, and then I do it again and copy and paste everywhere it says test, and I printed it twice. So that's one way, but that's a lot of work, right? Just to get one plot with some text on it. So we're gonna create a function, okay? And this function is gonna let us put in whatever we want. So we do have to change everything here. Good coding practices would say we should change all of our ERA, everything where it says ERA. We're gonna change this to a generic data frame. So what we wanna do is we have a function and it takes in a data frame. It could be called train, it could be called test, it could be called ERA, it could be called whatever, so long as the data is formatted the same way. And then it will access the same columns and print all the same information and make the same graph. But we only have to have one function, and we just have to switch out the data set, the data frame, okay? So we're gonna make this a generic, we're gonna make this a function. So the way you'd make a function is you type in def, okay? And I'm gonna say make correlations, make core. Okay, so def says I want to make a new function, space, make core, this is the name of it, colon. And now, similar to for loop, we're going to put everything under this indented as a function. Now, like I said, in order for this to work, it needs to take in a data set. So anytime I put in a data set, a variable, it's going to read that and then put it into everything else. So let's use the generic variable df, okay? So anytime I put in any data frame arbitrarily, it's going to use this and then populate everything else, okay? So the next thing we got to do, just like how in the for loop we had to have all of this indented, I'm going to select all my rows. I'm just going to type in tab. So now everything is indented one time. Okay? Everything is now indented one time. Right? You have this space. You have this space here. Okay. Now I need to change all the places where it says ERA with df, because df is our generic data frame. Why is it italicized? Because we're making a function and this is the variable inside the function, right? And this could be anything, right? It could be X, it could be Nick Wan is cool. This is just whatever your generic variable is. So just like how in Pearson R, we put in a variable here and a variable here, inside the documentation, this variable is like X, and this variable is Y, right? And the scatter plot's the same thing. Inside the scatter plot, or inside the KDE plot, there's a variable called data. This is just what the variable is, generically, in the function. So now we're gonna change all the places where it says ERA. This might take a while. Although if you know anything about multiple cursors, you could save yourself some time. I won't blow people's minds with multiple cursors today. Okay, so now we have all the places where it says, where it used to say ERA, it now says df. So again, we just took the code we ran before, we pasted it down here, and we said, we're gonna make a new function, we're gonna define our function, make core, df. Right, make core, and we're gonna put in a data frame. Okay, now if we run that, nothing happens because this is just creating the data frame. Okay, now if we make a new line and we take make core, okay, and we put an ERA, it should give us exactly what we did here because this was all based off the ERA data frame we made, right? So here we go, make core ERA, our first function, and look at that. We did all of those lines of code. We turned it into a function, and now we have one line of code, and it does all of that stuff for us. And it's the same as ERA up here. Okay, so let's do it again. And this time, let's do it with our new data set. Let's do it with train, right? We just made this called train. Random sample of 100. Let's do it. Here you go. So if you had a new data set and there was 100 rows, here's a different correlation. It's going to give you a different Pearson R's, Spearman R's, different R squareds. Let's do it one more time. Let's do this with test. A different set of 100 rows. Again, different R squared. Okay? So you can see here we replicated the stuff we were doing before. And with our new data sets that we created, just random samples, downsampled data, 100 rows here and 100 rows here, we now have 2 different ways, 2 different plots. Same info, it's all coming from here, but pretend this was 100 rows from a different season, or 100 rows from this current season. Your correlations might look something like this, right? Okay, homework time. Let's do all the stats, correlation, central tendency, p-value, t-value, all of that stuff again, except let's do it for strikeouts per 9. Let's use a new function, import a new stats function from the SciPy stats package called Wilcoxon, and then compare that. And then the graphs right now just say ERA times FIP, but it doesn't have like what the data set is. Let's try to make it so I could declare like what data set it's using. So you could put that anywhere in here, but let's try to include that in here somehow. That's pretty good for homework. True. Good job. Way to go today, y'all.